In this video, we will consider a simple harmonic oscillator. A simple harmonic oscillator is a mechanical system whose acceleration is the negative of a constant times its position. So we're looking for something that when we calculate its acceleration, we get minus times a constant, and it turns out there's my constant. And I'm going to give it a weird name, omega squared, and I'll tell you why later, times its position. Now, I said acceleration. It can be more generalized than that. This could be angular acceleration, this could be angular position. And in fact, in calculus, we can expand this definition to cover things besides just things in physics. But for us, this will work as our definition. Anything that obeys this type of an equation is called a simple harmonic oscillator. Now, it turns out simple harmonic oscillators are all over the place in our physical world. Buildings behave as simple harmonic oscillators. Atoms inside of a glass behave as a simple harmonic oscillator when you tap them. Crystals inside of electronic devices that are used as timing devices do this. In fact, what's really neat about this is the fact that this thing follows what is known as periodic motion. That is, it goes through a motion and then comes back and traces its footsteps, completes a cycle, and then repeats. And it repeats it with a fixed amount of time. So harmonic oscillators form the basis of all modern timing devices. So they're extremely useful to us. This omega that I've written, and which I'm going to squared, is a positive constant. It has a name. It's called the angular frequency. And if it looks something like the angular velocity, there is a connection between them that we'll show in a later video. Now, if you have something that has acceleration like this, it's not constant acceleration, so kinematic equations don't hold. There is a lot of math that goes into solving such a thing, but it's enough for us to know the solution. And the solution is that it repeats itself. And if we think about it for a little bit, we know that if you have a function like x squared, it doesn't repeat itself as you go in time. You think of other things. What is the function that repeats itself? Well, pretty soon you think, well, sines and cosines, they repeat themselves. And in fact, that is the solution. The solution to this can be written as either a cosine or a sine function, not a Cincy function. And so you can write it like this. X is equal to some number called a, which we'll talk about in a minute, times the cosine of this omega t plus some additional angle. This is called a phase shift. And this number there is called the amplitude. So this is one solution, but you could also write it as a sine of omega t plus some different phase angle. So either one of those is a perfectly good solution to the problem. Which one we choose will depend upon the problem at hand. Now I want to go back and look a little bit at what this thing says. Choosing one of these, whichever one that you would like, you have a function that's going to do something like this. Not very good drawing, I'm afraid. Let me try to do a little better if I can. So it repeats itself. This height here is at A. This bottom is at minus A. This height is called the amplitude. The cosine function goes between 1 and minus 1. If you want it to go bigger than that, you need to multiply it by a number. If you want it to go smaller than that, you have to multiply it by a number. This height is called the amplitude, and it goes from plus A to minus A. The 0 point is called the equilibrium position. The distance along here, where this is t, and this is x, this distance from, say, a peak to the next peak It's called the period. And it's the value that when you put in a big T here, that this will change by 2 pi, and the cosine function or sine function will repeat itself. This shift, where this cosine is no longer starting with its maximum at 0, is this phase shift, phi. Most important thing about it is it repeats, and it repeats itself with a fixed time called the period. And that period, when multiplied by this omega, gets 2 pi. Now, let's put some of these terms into our notes. Equilibrium, this is the position. About which the system vibrates. And by the way that we've set it up, it's been set up so that that position is at x equals 0. The displacement is the amount that the system is away from the equilibrium position. In other words, it's x. The amplitude is a. This is the maximum displacement. The period is given the symbol big T. This is the time it takes for the system to complete one vibration. Key thing about that is omega times T is equal to 2 pi. So if you know that constant omega, you know T, the period, and vice versa. Frequency. Sometimes instead of talking about the time it takes for something to make a vibration, if that time is very short, we instead count the number of vibrations that occurs in a given amount of time. This gets us to the frequency. The frequency is the number of vibrations a system makes in 1 second. Its units are hertz, named after Heinrich Hertz. Now, hertz is an inverse second. Key thing about this is that the frequency is equal to 1 over the period. This is really the definition of the frequency. So there's no way, none of these equations, F equal 1 over T or omega T equal 2 pi, these don't actually come from physics. These are basically definitions that come from trig and the definition of these terms. So they're independent of the type of oscillator you have. They will work for any type of oscillator you're given. Now, from these two, you can also see there's some other things that we can get out of this. For instance, F is related to omega by dividing by 2 pi. I get that by looking at these two equations here. Right? So, there are many equations that you can get. These are the three important ones that you should know. Alright, so what do we know? Well, we know that the answer is going to be a sine or cosine. We know that if you give us the a, that's the acceleration, you give us omega squared. If you give us omega squared, you have given us the period, that is the time between that the thing takes to make an oscillation. And if you've given us the period, you've given us the frequency. Let's see how we can actually put all this together in a problem. Let us assume we have a equal minus 9x. Then omega squared is 9, and that's 9 rad squared per second squared, I might add. Remember, this is in meters, this is in 1/second squared, acceleration's in meters per second squared. Therefore, omega would be the square root of 9 rad squared per second squared is 3 radians per second. T would be 2 pi over omega, would be 2 pi over 3 seconds. So slightly more than 2 seconds. You can punch that out in a calculator. And frequency would be 1 over t, would be 3 over 2 pi hertz. So if you give us this, we can find all of this stuff. And we know it fits a sine or cosine. The only thing left is to find that phase angle and the amplitude. Alright, this covers the basic ideas of the simple harmonic oscillator. We'll take a look at some special cases of oscillators in the next videos.